problem with an impossible looking radicand, and a lot of these problems just take advantage of the very elementary property that if you have the square root of something squared, I'll use question mark here. A question mark can be any type of expression. That's the square root of something squared is just equal to the something, right? And not all of these, but a lot of them are based on this very straightforward observation. Okay, squaring and square rooting are inverse functions. Now, the structure we have going here is, notice that 100 is equal to 31 plus 69. So we can write this radicand numerical form in the symbolic form, which is a little bit easier to manipulate the letters versus the numbers. Believe it or not, algebra sometimes is a lot easier than just trying to do the arithmetic directly. Now, most of this is pretty straightforward, tedious but not hard. We use the binomial expansion right here. Notice the presence of the binomial coefficients here. 4 choose 1 is 4, 4 choose 2 is 6, and you have that symmetry. All right, here you collect like terms. The very next line you divide by 2. So all of that is very routine, and we get something that we hope will factor, and it does, but it's not obvious why. Now the result that turns out to be useful is this slightly less popular result, the square of a trinomial. Now, a trinomial squared, I'll just write down the result here. I'm using Z here. Mark through it like that so it'll look like a Z and not a 2. And then we have actually 9 terms when you square a trinomial. And so they occur pairwise. The linear ones do at least. And so I'll write the 2 out front. Then you have what they call the elementary symmetric polynomial in 2 variables here. But it's just every possibility of combinations of pairs. Okay, so xy is the first pair. xz. Okay, we have xz right here. And then the very last one will be to pair up y and z. And it may still not be obvious. It wasn't to me either. I had to look it up. I didn't think to use this identity. But if you take a look, you can kind of see why this would be true. Notice right here that if you square a squared, you're going to get a to the 4th, right? If you square b squared, you'll get b to the 4th. And if you square ab, you'll get ab quantity squared. But then the rest of this stuff happens twice, and that's how you get all these other terms. Now notice there are 9 terms here. 1, 2, okay, 4, 7, 9 terms. It's just that some of them combine into like terms, okay? So this identity is why this entire piece right here, you see this entire piece actually factors into this, which I wouldn't just notice that. I wouldn't just notice that. This identity is what does the job for us, okay? But anyway, with that, we can move along, and you see we have what we're interested in written as a perfect square, okay? We have what we're interested in written as a perfect square. And so here's the original problem. Okay, it's written like this, but we've already shown that this object with the 2 gone is actually equal to a squared plus b squared plus ac, all quantity squared. And so I've just written all that down for you here, folks. 31 squared, not to the 4th, but 31 squared, 69 squared, and also the product of those 2 numbers, 31 times 69, you end up getting 7861. Okay, so y'all, that is the answer. And again, these problems are a little tricky because they almost cheat when they do these Olympiad problems. They start with some obscure identity or not so obscure, and they work backwards. Then you're supposed to figure out which identity to use. So I'm not super impressed with the problem. I know I wouldn't be able to figure out any of them, without looking at the solution. But in any event, that's the answer to the question. I hope you enjoyed.